Today we're going to talk about the colligative properties of solutions. Now, colligative properties are based on how the solvent and the solute interact, and we're going to see how that changes the properties of a solution or solvent. So a colligative property is any property that can change when the concentration of the solution changes. So we'll look at several examples. It depends on how many particles you add to the solvent. And what it's doing is it's changing the actual properties of the solvent. So most of the time we're going to be talking about how it changes the properties of water, like water's boiling point or freezing point or vapor pressure. So our first one is vapor pressure depression. Depression just means lowering. So if I add a solute to water, it actually lowers the vapor pressure. Now the vapor pressure is created by these water molecules or any solvent particles pushing back down on the liquid. So there's this equilibrium that's reached as the water molecules evaporate or vaporize, and then the water molecules that are up here are actually coming back down and forming liquid again. When you add a solute, those solute particles actually attract the solvent particles or attract water and keep them in the solution. It kind of holds them down or attracts them. A lot of times it's ion dipole interactions, because water is polar, it's a dipole, or often we use solutes that are ions, like sodium chloride. Or you could talk about polar compounds attracting water molecules. But it lowers the amount of those solvent particles, like water, that can escape the solution. Okay, boiling point elevation. Here you can see that the amount of energy necessary to allow the solvent molecules to escape will increase as you add a solute. Now this is related to vapor pressure depression. Because less particles are coming off of the solution. Okay. Here's the normal boiling point. Here's the elevated boiling point. Less particles are coming up. This lowers the vapor pressure. And in order for it to boil, the boiling point happens when the vapor pressure is equal to the atmospheric pressure. Now, if the atmospheric pressure is greater than that vapor pressure, it's going to be hard to get those particles to escape. So you actually have to add more heat. And so the temperature at which this solvent boils is going to increase. It's the reason why we add salt to water when we're cooking pasta. Adding that salt to water increases the temperature at which the water boils, so it's keeping those water molecules in there instead of letting them leave at 100, and the water will never increase past 100. It stays at 100. And so getting it to boil at a higher temperature is easier. Well, it allows you to cook your pasta faster. The third thing is freezing point depression. And here what the solute particles are doing is they're stopping the solvent particles, like water, from forming a solid. Okay. So they interrupt the hydrogen bonds in water in order for them to freeze and become solid. And so you have to actually give up more energy in order for that to happen. So it destabilizes the intermolecular bonds. This is the reason why people add salt to roads. The salt helps to break up the ice on the roads. It allows for the road to be at 0 degrees Celsius and still be the water to be on the road as a liquid instead of ice. We add antifreeze to our cars. It's ethylene glycol in water. That's our solute, the ethylene glycol. The reason why we add that to our radiators is because we don't want our radiators to freeze. Adding that solute helps to lower the freezing point, and so your car won't freeze over at something like 0 degrees Celsius, or 32 degrees Fahrenheit, which we rarely see here in California. It also helps with overheating. If you add the antifreeze, now it's increasing the boiling point, and so it will boil at a much higher temperature and won't leave the radiator. It won't evaporate away. Here's the actual chart, what you see how it protects it. It could, let's see, go from freezing down to -34 degrees Fahrenheit and boiling up to 265 degrees Fahrenheit. Okay. We're going to look at the difference between sugar dissolving and salt dissolving. So salts are ionic compounds, and when they dissolve, they completely dissociate, meaning they break apart. All of the negative ions get surrounded with the positive ends of water, and all of the positive ions get surrounded with the negative ends of water. When it comes to sugar, those molecules stay intact. They're pulled apart because they're polar and they attract the water molecules, but the molecules of carbon, hydrogen, and oxygen that are in the sugar molecules do not come apart. Okay. This is going to play a role when we're looking at calculating the freezing point and boiling point of a solution. Now, first we'll talk about the Van 't Hoff factor. The Van 't Hoff factor is just how effective that solute particle is at lowering the lowering the freezing point or increasing the boiling point. So here I've written a solute that dissolves into more particles is more effective. It's better at doing those things, changing the boiling point or freezing point. Breaking down into non-electrolytes, so things like sugar, they're covalent molecules. They're made up of nothing but nonmetals, carbon, hydrogen, oxygen. Those remain intact when dissolved. They don't break up. So when you're looking at the Van 't Hoff factor, this would just be one particle. Electrolytes are ionic compounds. So these ionic compounds, remember, are made up of a metal plus a nonmetal, or we could have a polyatomic ion somewhere in there. These will dissociate, they will break up into ions when you dissolve them, and so you'll have, instead of one particle, you'll have at least two, maybe more particles. So we'll look at counting particles. And remember, this is going to determine how effective that solute is at changing the boiling point, freezing point, vapor pressure. Okay, so here we go. First one, sodium chloride, NaCl. We have to decide if this is an ionic compound or a covalent compound. So we have a metal plus a non-metal, and I know that metal plus non-metal is ionic. Now, how many particles is this? I like to draw a line to figure that out between the metal and the non-metal. Remember that capital letter, lowercase letter, that's the element symbol, just one element symbol. And so here I have sodium plus chlorine, that's a total of 2 particles. It'll break down into sodium ions and chlorine ions. Okay, this next one I have non-metal. This is hydrogen, that's also a non-metal. Oxygen, non-metal. Hydrogen, non-metal. So this is nothing, excuse, that's really scratchy. This is nothing but nonmetals. So all nonmetals is a covalent compound. That's not an electrolyte, so it's just going to be one particle. Okay. So we can do the next one. So you've got carbon, hydrogen, and oxygen, again, all nonmetals. So covalent, one particle. Then we've got sodium hydroxide. See if you remember that one, hydroxide. I know right away, because this is a metal, that this is ionic. So if I draw a line after the metal, I can see sodium. This is a polyatomic ion. This is not going to break apart. It's going to stay as a polyatomic ion. So I have sodium and hydroxide. That's 2 particles. Sodium ions and hydroxide ions. Okay. Over here we have magnesium and bromine. Magnesium is a metal, so I'll draw a line after the metal, and I'll see I have 1 magnesium, and then bromine, I have 2 bromines, so that is a total of 3. And that was 1 magnesium, which if I look on the periodic table, it's in group 2A, it's 2 plus, and 2 bromines. Bromines in 7A, it's a 1 minus. Okay. Next one, carbon and hydrogen, both nonmetals, 1 particle. Done. Next, potassium and what is this? Sulfur and oxygen. Oh, there's something in there that you should remember. Let's see. If I draw a line after the metal, I can see I've got metal plus. This is more than just being a nonmetal. This is 2 capital letters. This is a polyatomic ion. So I have 1, 2 potassiums, and then this is going to remain intact. Remember, these are polar covalent bonds. That's the sulfate ion. So that's going to be a total of 3 particles. 2 potassiums and 1 sulfate. Okay, some more examples of colligative properties. So some that we're not going to get into too much detail, but the first one is color. Remember that a colligative property depends on how much of the solute particle you have in there. So if I'm adding, let's say, Kool-Aid powder, purple grape Kool-Aid powder, and I keep adding more and more and more, the color is going to be darker. So it's changing as my concentration is changing. The other thing is taste. So same thing, if this was Kool-Aid powder, it's going to get stronger in taste. Or if I'm diluting concentrated orange juice, the taste is going to change. So it's a property that will change based on the concentration. And then the last one is density. And here's an example of that. I've got added salt to see how much I can get this egg to float. And so the water is changing in density with the added amount of table salt. Okay, and the next video we will talk about performing calculations with these.